You guys can ask.
You're just
If you-
concentrating on food, so you just don't.
Yeah,
But I mean, you.
food is tough here than that stuff.
But if you want to get extras, then they say can't get extras. That probably should tell you.
Well, then some
Okay,
will
I'd
let
let
you
you
get
get
extras.
extras.
They'll
You get
let you
extras
get
if you're
extras. They're not supposed to, but they do.
Okay.
Go tell you to put it back. Yeah.
Except the middle age.
Except for the middle lady. You never
She'll like take the hamburger off your tray.
Sorry.
Well, you can't go to Dairy Queen and get it on credit. You can? You can go to Dairy Queen and not pay any money, being negative.
No, it's Sonic. You can reuse the coupons that they give you.
Yeah, you just don't show it to them.
Yeah, they don't.
But what I'm saying is they don't have money. You can't buy any food. Okay,
My card just gets declined.
That's so bad.
you have a card.
I've never had that problem.
Neither have I. It's supposed to be used for gas, but.
You spent it at Casey's this morning.
What'd you get at Casey's? Donuts and
No,
coffee.
I got chips. I got pizza rings and Laffy Taffy.
This is all recorded, so
Oh god.
No, it's not.
it's recording.
Put it in a jug.
Oh, Daddy Barner.
Okay, so this is the first one, and that would be the dot structure. Everything has to have 8 around it. Some of you are getting, I don't know if you're just not knowing how to do it or you're getting lazy, but if you give me a structure that doesn't have 8 around everything, it's going to be wrong. Okay? You've got to use up all the electrons, and to do that, everything's going to have 8, whether it's multiple bonds or not. So this would be the dot structure, and then this is the structural formula. Well, we learned that already. Now we're just learning shapes. And so if you look at the shape, it kind of has something to do with the name. So this kind of forms a triangle down here. Okay? So it's probably going to be what? Trigonal, planar, or trigonal pyramidal. So why would it be trigonal pyramidal than planar? Yep.
Because it has the like ones on top of the P or whatever, so it has the little extra ones.
Yep. So this pair, now this is a chart. If you guys like to memorize chart, here's a chart you can memorize if you want to do it. But I think if you have it drawn out, you can see it's a triangle. This pair of electrons is going to force these 3 pairs, because that's actually what they are, force them down. Force them further away from one another, from this top pair. So it forms a triangle at the bottom, and then this is at the top. So this is trigonal pyramidal. Does that make sense? If you want to memorize that chart, it says if you have 4 groups of electrons around the central atom and 3 atoms, and that tells you what it is. Okay? But if you're like me, try to make it simple. Okay? Simpler the better, up to a certain point. Some things you can't make as simple as you'd like. Okay? You can look off your chart and look for something that has 2 groups of atoms around the central atom and then 2 branched atoms. That says it's linear on that chart. But what you can do is you can also think, how far do these 2 groups, can they get away from one another? And it's 180 degrees. So that would make it linear. Does that make sense? So that would be a linear structure. You should have that written down as linear. All right?
Yeah.
This one here,
Oh my god.
okay? This one here, you have 4 surrounding the center. So this is the one that's tetra, 4. Okay? That's what tetra is a prefix for. Tetra means 4. 4 bonded atoms. So this is tetrahedral structure. Okay? Got a triangle base, and then it's got the one, whatever one you want to look at, that's extending upward. So that's a trigon, or that's a tetrahedral. Tetra is 4. Okay? Did anybody ask anything about that in your math classes?
Our teacher was gone yesterday.
Mick was preaching about
Except Decker doesn't really know.
About what?
sectors.
Sectors. Yep. Okay. This would be a one that's a little tougher. But if you've got 2 atoms off the center, it's either going to be linear or bent. Okay? if you got two atoms off the center one, there's only two shapes it can be, linear or bent. Now this one is bent because this pair is forcing these two closer together. It would not be 180 degrees. Okay? It would be less than that. So that's why it's bent. This one is bent. Okay? Did everybody get through those first four then?
Yeah.
Writing them out? Okay.
Yes.
So then the last two you might just look at it and then see if it makes sense if you weren't able to do it. In fact, this one's really easy to do. This would be your structure. This would say 4 groups of electrons around the central atom and then 2 atoms branched. That's bent. But you can kind of see that because all of these have to get, far enough away from one another. It's going to push these 2 atoms closer together. So that one's bent. Last one. Okay, and then we've got the last one to go through. This would be the last one. And this is trigonal planar. Now, the reason why it's trigonal planar, we have 3 pairs around the central atom. They try to get as far away from one another as possible, and that would be 120 degrees, even though I'm not showing 120 in this example. But that would be trigonal planar. And if you look on your table, there's 3 groups around the central atom and 3 branched atoms, and that's always trigonal planar when that happens. Okay, I'll leave that up there. I'm going to share with you a site that some of you like extra practice. Some of you will never use it, okay? It's just preferences some students have. They want to be prepared. Sophomores tomorrow will be taking a quiz over this stuff that we've been doing. The dots and the lines. Okay?
We can name them.
And you'll have to name them.
Just sophomores.
Juniors are going to take a practice ACT science. Okay. So, I can have you go to a site here. I'm going to show you a site here in a second that you guys can go to and access and practice as many as you want. Okay? Some of you don't take advantage of that, and because of that, you just don't have as many to practice, and some of you don't need any more practice, and some do. So if you think this would benefit you, this might be a good place to go in which to get that extra practice that you need. So, on the website I have this site. I have it linked. And so then the first thing you would do is you'd go, I'm going to do a tougher one than that though. So, trouble with this site, they include a lot of things that you're not needing to know, or a few things you don't need to know. So, like if I was doing this one, I'd do it on paper and I'd go, well, sulfur has 6, fluorine has 7. Then you would go ahead and put sulfur in the middle, surrounded by your fluorine. Do your pair, count them up, there's 20. So then there's 4 take away, you get 16. Then surround the outside first. That takes away 12. We're left with 4. Put them off the center, we're out. So 6. So we got 20. So then you go, well, I want to see if I got it right. So then you'll go down here and go, yep, let me see, reveal structure. And it reveals it for you. And it's basically the same thing as this, the positioning of the fluorines are off. So then you go, you know what I really need to practice is the names because we just started going through there. So you drop down, you got all these names. Some of these names don't agree with that. You haven't seen these names before. So the octahedral, the seesaw, the square planar, square pyramidal, T-shape. Those there that's when they disobey the octet rule. But the rest of them, kind of trigonal bipyramidal is not, of course, one of those examples. So then you look at your structure and you say, what kind of structure it is it? And you say what? Bent. So we'll go bent. We have to do it under the molecular structure. The electronic structure would be looking at these, and I'm not going to ask you questions on that, that would be looking at all these groups. And that forms a tetrahedron. Okay, but so I don't ask you about that. So I'm going to grade it. And the bottom one's correct. The top one I don't worry about. Does that make sense? So the trouble is when you get into these, it may give you one that is not, doesn't obey the octet rule. For example, this one. What's wrong with that one?
There's not 8 electrons.
There's not 8 around boron. And boron's one that doesn't have to have 8. So if we would go further in AP chemistry, we would talk about elements that don't need 8. They have fewer or they have more. They have 10 or 12 or something like that. This would actually be a trigonal planar is what that would be. So be careful because you can get into those examples where they're, like this one would be one that does not agree. So you reveal the structure.
What?
Hold it right there.
Okay. So that one has 5. They have 10 electrons around the central one. Well, you know, if you get one like that, that's the only problem with these sites. It doesn't limit it to only what we're studying. So that's the thing you'd have to do. Is just, you know, if you get one, you can go ahead and practice those. Okay. All right. Let's see. Let's take a look at the new information. This is really pretty easy stuff. We're gonna use somebody's board, and it's probably somebody's in here.
You still have those?
Uh-huh. Is this yours?
Yeah.
All right. It's got good information on it, man.
You guys did.
Whoa.
Good information.
Mesmerizing.
Whoa.
Wow, that hurts.
Yeah, that hurts.
I think that light's good.
Stop.
He's a little.
Your table's always in there.
Circles are nice and circular.
Now it just messes
Circles
with
are
my
nice and
eyes.
Okay. We're going to talk about this term electronegativity. And it's something that really, when we did the trends where increases and decreases, really didn't know about electronegativity much other than what we were reading and what I told you about. Now we're using it. Okay, now it's very important to kind of know what electronegativity is. So there's the definition, and this tells you about the ability to attract shared electrons. So that's what we've been doing, right? We've been putting electrons in between atoms and they're sharing. So it's like, oh, now I get it. Now I know electronegativity stands for a little bit more. So then as the period trend is to do what, according to this table? What's it do? What's the trend? It increases, right? So the period trend for period 2 and period 5 is to increase going across. We are only showing the S and P's. We're not showing the D's in the group period 5. We eliminate those. We don't worry about those. Okay. So then electronegativity says if you have a big number, what kind of attraction do you have? Big number, what kind of attraction? Big. Okay? If it's a big attraction for 2 electrons, for example, if we have lithium and fluorine that we're going to show bonded on, we won't show lithium and fluorine probably bonded on this way because, and we'll explain why in a second, but if we show those 2 bonded, fluorine is 3.98 and lithium is 0.98. So fluorine has so much of a bigger share. So it's kind of like this. Lithium lost that electron. So what charge is lithium?
Positive.
Positive. Loses a negative. It's got more protons than electrons. So it's positive. What charge is fluorine? Negative. This is not covalent bonding then. Okay? If I put lithium and fluorine together, there's so much of a discrepancy in their sharing, it's really not sharing anymore. It's fluorine basically has the electron and lithium doesn't. So lithium gives it up, fluorine takes it, and then we know those charges get together and we have lithium fluoride and we can name it, right? So that's the case. Sometimes when there are big differences, we call them ionic when they get those big differences, okay? So what we've been doing is we have not been using metals in drawing our molecules, right? They've been all nonmetals. Been nitrogen, fluorine, chlorine, bromine, iodine, carbon, nitrogen, all those. So if you notice, what do you notice about the nonmetals up here? So this would be, this here is, I guess carbon would be considered there too, but this is kind of the nonmetal section there, and then this would be, so what do you know about the nonmetals? They're all high, right? They're all pretty high. Carbon's a little lower, but they're all pretty high. So they all want the electron, so they share that electron, okay? So how do they share? Do they always share equally, or how does that come about? So let's say we put fluorine and bond it on to oxygen. I'm going to say, yeah, we'll go fluorine and oxygen. Okay, we'll just show that bond. Between those two, which one has a bigger share of the electron?
Fluorine.
Fluorine, bigger number. Does that make sense? Fluorine has a bigger share. Now, the difference is 0.54. Not a big difference, but a little bit of a difference. This is going to create what we call a polar bond. Okay? And we'll talk about polar bonds in that. So basically, fluorine has a bigger share of the electron than oxygen. It creates a polar bond. So polar means opposite charges on either side. Okay? So which one would have a stronger polarity if we compared these two? So fluorine's 3.98, nitrogen 3.04. That's a difference of 0.94. The difference between those is 0.54. So which of these two do you think would have a stronger polar bond? F and N or F and O? Where you have the bigger difference. F and N. Bigger difference. So that's going to create a bigger difference in the polarity of it. Okay? Now, what if we have fluorine bonded to fluorine? What's the difference? Nothing. So there's no polarity. They have an equal 50-50 share of that pair of electrons. So this would be called non-polar. This would be slightly polar because it's like 0.58, and this is even more polar because it's 0.98. So how far do you go in difference to know that it's polar, non-polar, ionic? That's what I'm going to tell you now. Okay, does that make sense? Is that the bigger the difference of nonmetals, the more polar that bond is. Polar means that one side is going to be slightly positive, and the other side is going to be slightly negative. Here, they're neither one. They're the same. Okay? Same with this. It would be slightly negative, that's slightly positive, and it creates a polar molecule, or a polar bond. If you guys would turn over to page 295. They give you a little table that really is a good indicator of what we mean by nonpolar, polar, and ionic. So, by looking at the colors and the shapes, if it's nonpolar, there's no difference between the two atoms that are bonded together. If it's polar, there's a little bit of a difference. And if it's ionic, they're basically separated from one another. Okay? All right. So that table was really helpful. You guys can look on your periodic table. Once you get your periodic table out, it's got electronegativities on it. Okay. So you guys, can you find electronegativity? It's on the back side of the normal side that we use, and it's in the upper right-hand corner is electronegativities. And so like for fluorine, you can see it's 3.98. When you look at oxygen, you can see it's 3.44. Nitrogen is 3.04, and so on and so forth. Okay, gives you all of them. So if you need to look them up, you can, which you will have to look up from time to time. So the note portions, not a lot of notes. This take about 5 minutes. Okay. There's two types of covalent bonding. One is labeled nonpolar. Nonpolar means there's very little difference between the two bonded atoms' electronegativity. When there is a small difference, so you're saying, well, small is relative. What does that mean, small? It means if it's a difference between 0 and 0.4 in their values, then you would call that type of bond nonpolar. So my example I have is selenium and sulfur. Selenium is 2.55 on your chart, and sulfur is 2.58. So the difference is basically 0. It's 0.03, but it's basically no difference. So that would create a bond that we would consider nonpolar. Okay? It would be kind of like a really, really, really weak magnet that's lost all its magnetism. It would not be magnetic for the most part because it really wouldn't work what you think a magnet should work. So that creates a non-polar covalent. Right? So that's what you're looking for, a 0 to 0.4 difference. Now, the reason that we're deciding if they're polar or non-polar covalent, we have molecules that will be polar molecules or non-polar molecules, and it makes a big difference of how they behave, chemically and physically. And so we're going to use those characteristics to understand how molecules behave. Okay? And it's based upon the bond types that are found in the molecule. Okay? The second one is called polar covalent. Now, polar covalent is where we have a bigger difference, but they're still nonmetals. Okay? The key is they're two nonmetals. We've got to always look at nonmetals as being covalent, and that's what we've been modeling in that. So the next one that we're going to show is going to be polar covalent, and if you look on that chart in the middle, the difference is 0.5 to 1.8. Okay, and I'll put that up here in a second because some of you are still writing down. I understand that. So the next one that we look at a difference that's bigger, and it falls within the range of 0.5 to 1.8. Okay. So here are examples of that taking place. So polar covalent is where you have a bigger difference. The example I give you is fluorine and nitrogen. One's 3.98, nitrogen is 3.04. The difference is 0.94. So it falls in that range. Now, the bigger the difference, the more polar it is. You got to understand that too. We're just saying that they're all equal in polarity, and that's not the case. So the bigger the difference in electronegativity, the more polar it will be. Now, over here I have the subtraction. That's the difference. So, but there's something kind of unique to this one that I didn't show on the previous example. So I'm going to let you write it, and then I'm going to talk about what the top and bottom represents. Okay? Because you're going to have to do the top and the bottom, both of those two, in which to represent something polar. So, this is supposed to be kind of like an S. It's a Greek symbol called sigma. If you want to know what it actually is supposed to look like, I'm not a very good drawer of a Greek symbol, sigma, but top of page 295 shows you what that's supposed to look like. Sigma negative, sigma positive. So the negative is on the side that has a bigger electronegativity, and the sigma positive is on the side that has a lower electronegativity. So that's how you decide the sign, negative or positive. Bigger electronegativity, negative. Smaller electronegativity, positive. Also, underneath is another way that you can describe it. And I like this one better, but you draw an arrow. The arrow will go toward the side that has a higher electronegativity. I think they might use this in magnetism sometimes. So then the side with the arrow has a bigger electronegativity, and the side that has the tail of the arrow, which looks like a plus sign, is the positive. So that's the other way in which you can represent it, one of those two ways. And I just wrote this up here just to kind of see how it applies to the bottom one here, where we put in the negatives and positives in the arrow. Okay, questions on that? So that would be that's how you would show a polar bond is underneath, or by the side of where you have a line, you'd show the arrow or the sigma positive and negative. Okay? Then, of course, if it's over 1.8, we know it's what? Ionic. So anything that we have a difference that would be addressed by a bigger electronegativity would be ionic, because it forms anions and cations. And usually it's a metal and a non-metal. And that's how we usually can tell without looking them up, the electronegativities up. So, okay, and then that's your assignment there on the board to do problem 296, or page 296, problems 28, 30, and 32. And you just use your electronegativities on your periodic table to answer those questions. Yeah, and it's a really short assignment, and we'll just have it due on Thursday, just because tomorrow when you guys come in, there'll be laid out quizzes for the sophomores, and then for juniors they're going to be taking practice ACT. When you're done, since they're doing the practice ACT, it doesn't mean you can talk and visit. You can either work on this assignment or work on something else of your choosing, okay, for tomorrow.